3. This first section is we're going to do 3.1, which is a review and preview. Then in 3.2, we are going to talk about measures of center, and in 3.3, we're going to talk about measures of variability. Remember from chapter 1, when we talk about characteristics of a parameter, talking about characteristics of a population, those numbers are called parameters. When we're talking about characteristics of a sample, those numbers are called statistics. And we talked about appropriate sampling methods, and most of the time a simple random sample is going to be your best sampling method. All of the statistic calculations that we're going to talk about really are only appropriate for simple random samples. Now in chapter 2 we talked mostly about the shape. So what we're going to do today is we're going to put numbers with center and we're going to put numbers with spread. Now we are going to look at mean, median, standard deviation, and variance in this section. In the next section we will talk about other important statistics in ways we describe sets of data. And so it's very important that you understand and interpret these important statistics. Now what we're doing is we are doing descriptive statistics in this chapter. That means we are simply summarizing or describing the important characteristics of our data sets. What we'll be doing in the second half of the course is we will be using inferential statistics, which means we are going to use our numbers to help us make generalizations about a population. We're going to use our numbers to help us make decisions. So the first thing we're going to talk about are measures of center. Now, there are different measures of center, some of which you have used quite often in your life and others you have not. There will be some that are mentioned in your textbook that we are not going to talk about. So we are going to look for that typical member of the data set. In your book they use the examples of chocolate chip cookies. And one of the things that must be done when we are doing this is we have to accurately define what our variable is. So the first thing we're going to talk about is we're going to talk about the arithmetic mean. And the arithmetic mean is the average that you have used most of your life. Now, in statistics, an average means any measure of center. So we need to use more specific language, and when we are going to add up our members of our data, their values, and divide by the number in the set, that's called a mean. And it's important that you use the right vocabulary in the right context. Here we have a comic strip that kind of talks about the difference between average and mean, and I will leave you to read that yourself. Now we have some important data, and we will look at this first symbol, which looks like a real fancy capital E, is a capital Greek letter sigma. And when you see that in front of something, that means you add up whatever follows. So sigma means sum of. We're going to talk about x as our variable. Sometimes we will put a subscript of I behind it, meaning individual x. A lowercase n represents the number of data values we have in the sample, and a capital N represents the number of data values we have in the population. When we talk about mean, we're going to use the symbol, an X with a bar over it. And we usually say X bar, or I will say mean. And X bar is the sum of all the individual X's divided by the number in the sample. When we are talking about the mean of a population, we use the lowercase Greek letter mu which looks a little bit like a U, we use that to mean. And that means we're going to add up all the individuals in the population and divide by the number in the population. One of the things that we look at, and one of the things we try to do in statistics, when you use the regular alphabet, that stands for a statistic. When you use the Greek alphabet, that stands for a parameter. So both of these stand for mean. X bar is the mean of a sample, so it's a statistic. Mu is the mean of a population, so it's a parameter. Now, the mean is reliable, and when we look at samples, the mean does not vary as much as some of the other measures of center, and this is because it takes every data value into account. One of the disadvantages is the same as its advantage, is that it's sensitive to every data value. So one extreme value can affect it dramatically. In statistics, this is called resistance. So the mean is not a resistant measure.
Let's just look at an example of how the mean can be affected by outliers. Let's say I have 4 children in the room. I have a 3-year-old, a 4-year-old, a 5-year-old, and an 8-year-old. I want to find the mean of this data set. So this will be set A. So the mean of set A will be 3 plus 4 is 7, plus 5 is 12, plus 8 is 20, divided by 4. So the mean age is 5 years. Now, let's say that in set B I have these same 4 children. And I have a 10-year-old come in. No, I don't want to do 10-year-old. I want to do, well, yeah, we can do 10-year-old. Okay? So the mean of B is going to be 30 divided by 5, which is 6 years. So this older child comes in, is quite a bit older than the first 3, and does raise our mean age. But let's say the 10-year-old goes away, and we have a 30-year-old come in. So now the mean of set C is going to be, I don't think I did this very well, 10 plus 30 is 50 divided by 5. So my mean age for those 5 children went up 10 years. So notice that the difference between set A and C is only that 30-year-old, but that 30-year-old coming into the room raised our mean by 5 years. So this is what it means to be a non-resistant measure.
Now the median is the middle value. When you put your data values in order, then the median is the middle value. Your book uses X tilde, a squiggle line above the X, to stand for median, but in a lot of textbooks it's denoted by a capital M. The good thing about the median that it's not as affected by extreme values, so it is a resistant measure of center. So what's true about the median is half of the ordered values are less than or equal to the median, and half of the ordered values are greater than or equal to the median. So again, the big difference about median is you must put your data values in order. If the number of data values is odd, your median will be a member of your data set. If your number of values is even, the median will be the average of the two middle ordered values, which may or may not be a member of the data set. So the first thing we do is we sort the values. Then again, if the data values, number of values is odd, the median will be in the middle. If it's even, the data value will be the mean of the two middle numbers. So you find the two middle numbers, add them up, divide by 2. Here is an example of a formula, but it's L of M. L meaning location. So this tells you how you find the location of the median in your data set after it has been put in order. So you take the number of the data values plus 1 divide by 2, and that gives you the location of the median. So for instance, if I had 25 data values, 25 plus 1 is 26 divided by 2. So the 13th value from the top or the 13th value from the bottom will be your median. So here's an example of a data set, and you'll notice they're not in order. So the first thing I must do is put them in order. Now I have 6 pieces of data. So I'm going to do 6 plus 1 is 7. 7 divided by 2 is 3.5. So my median is going to be halfway between the two middle values. So what I'm going to do is I'm going to add those up, which I'll get 1.83, and then I'm going to divide by 2. And that will give me my median, which is 0.915. So now I have a second set of data, and you can see from this one I have 7 individuals in my data set. So I'm going to do 7 plus 1 divided by 2, which is 7 plus 1 is 8. Divided by 2 is 4. So once they're in order, it's going to be the 4th data value. So my median is going to be 1, 2, 3, 4 from the bottom, or 1, 2, 3, 4 from the top. It doesn't matter that we have 2 that are exactly the same. So in this one, the median is 0.73. It is a member of our set. Now the mode is the value that occurs with the greatest frequency. The data set can have one or more than one or no mode. What happens with the mode is it really isn't very useful, so we don't use it very often. Your data set can be bimodal, meaning that it has 2 values that occur with the same frequency. It can be multimodal, that a whole bunch of values occur with the same frequency, or it could have no mode in that no data value is repeated. The mode is the only measure of central tendency that can be used with nominal data. So if we were looking for eye color, or we were looking at our M&Ms, the color that happened most often is the mode, and that's really the only measure of central tendency that we can use. For example, in set A, you can see that, and in looking at that, I see that 1.10 happens twice, so that's the mode. Notice that in data set B, 27 happens 3 times, 55 happens 3 times, so it's bimodal, it has 2 modes. And notice in set C that no number happens more often than any other, so we say it has no mode. Now the mid-range is halfway between the maximum and minimum values, and I will tell you that you don't use that very often at all. So sometimes it's kind of nice to know where it is, but because it only uses the maximum and minimum values, it is very rarely used. So we take the maximum value, add it to the minimum value, divide by 2. It is very sensitive to extremes, but it is very easy to compute. It reinforces that there are several ways to define the center, and this does avoid confusion with the median because now we're looking at the distance from the mid-range to the maximum is the same as the distance from the mid-range to the minimum. Where remember with the median, you had the same number of data values above and below the median. Data values, not distance. Okay. We are going to put in a slide here for round-off rules because now that we're doing calculations, that's going to be important to you. And I will tell you, most of the time, our round-off rule is carry it one more decimal place than is present in the original set of values. So if your data set is rounded to the nearest 1, you will round your calculated value to the nearest 10th. If your data set is rounded to the nearest 10th, you will round your calculated value to the nearest 100th. So when we find the measures of center, we want to think whether the results are reasonable or not. Let's think about the method used to collect the sample data, because that really does tell us what measure of center is most appropriate. Now, what do we do first? When we want to talk about the mean, we find the sum of all the values, divide by the number there are. It's sensitive, and sample means tend to vary less than other measures. When the mean doesn't make sense for some reason, or the data is very skewed, then we may use the median, because then that tells us the number of data values above and below the median is the same. For instance, if you're going to buy a new house in a new community, the data that the Chamber of Commerce reports is the median value, meaning that half the houses in the community cost more than that value, half the houses cost less than that value. The mode is sometimes useful. It's the one that occurs most frequently. It really is good when you're using nominal data. And then there's the mid-range. That's easy to compute, but very rarely used because it doesn't give us a whole lot of information. Now let's talk about the shape of the data, which we talked about in Chapter 2, but remember, we have symmetric distributions if we can fold it in half and both halves are roughly the same. We have skewed when they're not symmetric. So remember, this one where the tail extends to the left is left skewed. This one that the tail extends to the right is right skewed. Skewed to the left is also called negatively skewed, and skewed to the right is also called positively skewed. The mean and the median are in different places in different types of distributions, but it is not always sure. It gives us hints. So when we have a symmetric distribution, the mean and the median should be close together. In fact, when we have a very symmetrical distribution, the mean and the median are the same. In a skewed distribution, because the mean is not as resistant and is affected by outliers, the mean is pulled in the direction of the extreme value. So, comparing the mean and the median. The mean is very influenced by outliers. The median is resistant, less influenced. We use the median when typical is needed, half above, half below. We use mean when the total is important. So for instance, the Chamber of Commerce will report the median housing price, but the tax assessor talks about the mean housing cost, because to the tax assessor the total value of all the homes in the city or county are very important, because the assessor wants to take the mean times the number of houses and get a value. And so both the mean and the median are measures of the middle, but they are useful in different ways. Now, when we look at skewedness, remember in a symmetric distribution, the mean and the median are in the same place, and the mode. When we have a skewed distribution, the mean is pulled, so the mean will be less than the median. The mode is always where the peak is. So the mode really doesn't give us too many clues. Other than when both the mean and the median are less than the mode, it gives you a clue that we have a negatively skewed distribution. When we have a positively skewed distribution, the mean is pulled further out in the tail. Now the median is going to be where we could balance this distribution. So if we cut this distribution out of foam core board and we tried to balance it, the place it's going to balance is at the median, because you basically have half of the distribution above and half of the distribution below. So we have talked about measures of center, so we've talked extensively about mean, median, and mode.